And then we want to find out if g is concave f. So g is the integral from 0 to x of f. What is g prime then? Just f. And what is g double prime? So we want g double prime, which is f prime, to be positive, to be concave up. So anytime that the slope of this thing is positive. So -4 to -2. And 2 to 6. Other than that, all the slopes are negative. Everybody agree with that? Yeah? Okay. Part B, we got a new function, capital P of x, which is capital G of x times f of x. We're going to find P prime of 3. So P is G times f. P prime of x then ought to be G of x times f prime of x plus G prime of x times f of x. Just using the product rule, right? And we wanted to evaluate this at 3. Does that sound right? Was it 3? Yeah. So G of 3, f prime of 3, G prime of 3, f of 3. So let's find all those things. First off, G of 3. G of 3 ought to be the integral from 0 to 3 of f of x. And what is that? From 0 to 2, those two triangles are going to cancel out, right? So really, we're just looking at 2 to 3, and it's below the x-axis, so it'll be negative. It should be a base of 4, another base of 3, divided by 2, multiplied by the height of that trapezoid, gives you -7/2 for G of 3. So we got -7/2. Then we need f prime of 3. F prime of 3 is the slope of f at 3. So what's this slope here? 1. So f prime of 3 is just 1. G prime of 3. Well, G prime of 3 is just f of 3. And f of 3 is -3. So we got -3, and then we have another f of 3, which is 3. So we got -7/2 plus 9, which should be what? 11/2. Everybody good with that? Any questions there on that? Everybody in Zoom good there?
Yeah.
Wonderful. All right. Part C. Find the limit as x approaches 2 of g of x over x squared minus 2x. So g of x over x squared minus 2x. That should be g of 2 over 0. If we go back and look for what is g of 2, that's the integral from 0 to 2, which is 0, right? We said those little triangle pieces already cancel out. So this is 0 over 0, which tells us this is indeterminate, which tells us we should use L'Hopital's rule. This is the AP test right now, so you will indicate that you're using L'Hopital's rule by writing out using L'Hopital's rule. This becomes the limit as x approaches 2 of g prime of x over 2x minus 2. And now g prime of 2 over 2. What's g prime of 2? That's the value of f at 2, which is -4. We get -2. Everybody good with that? Zoom, are you all good with that?
Yes.
Wonderful. All right, and then part D, find the average rate of change of G on the interval -4 to -2. So the average rate of change of G ought to be G of 2 minus G of -4 over 2 minus -4, which ought to be something over 6. We got to figure out what g of 2 is. Well, we already did that, right? G of 2 is 0. Minus our value for g of -4. So g of -4 ought to be the integral from 0 to -4 of f, which ought to be the opposite of the integral from -4 to 0 of f. The integral from -4 to 0, that's just a triangle and a trapezoid. So we'll do a triangle and the trapezoid. 1/2 base of 2, height of 6. And then the other one is base 1, 6, plus base 2, 4, over 2, times the height of 2. So we end up with, what do we end up with? -16 is our final value for g of -4. (16 over 6), which is what? 8/3. Everybody good with that? Zoom, are you all good with that?
Good.
All right, then it asks us, does the mean value theorem guarantee a value c on -4 to 2 for which g prime of c is equal to this average rate of change? So the mean value theorem for g tells us that g, if we were to use that, it would mean that g has to be continuous and that g has to be differentiable, right? So our question is this continuous and is this differentiable on the interval from -4 to 2, right? And so first off, does the derivative of g, which is f, exist everywhere from -4 to 2? It does, doesn't it? So what does that tell us about g? That g must be, it must be differentiable, yeah. And if the function is differentiable, then it must be continuous, right? So if a function is differentiable, which this one is, the derivative is defined everywhere from -4 to 2, then it must also be continuous. So we would say, yes, the mean value theorem does apply. There must be some place in there where the value is whatever it was, 8/3. Right? Or the value of f is 8/3. And we can see that there is somewhere in there, right? 8/3 is like right there. Everybody good with that or no? Y'all here good with that? People at home, you good with that?
Yep.
Was that a yep? Yep.
Yep.
Yeah, that's what I thought. I couldn't tell if it was yup or yep. So that's why I asked, but we'll just stick with yep. All right. Number 5. How'd this one go? Good or no? Good until C? Also good until C? Or just good? Think good? Good until C. Okay. All right. So for part A, we're writing the second degree Taylor polynomial for f about x equals 1. So that should start off with f of 1, which is 4. Then it should start off with f prime of 1, which is, should be what? 0, right? Because natural log of 1 is 0. And 0 times something else is still going to be 0. So no x term. And then f double prime of 1 is 4. So plus 4 times x minus 1 squared over 2 factorial. Or if you chose to write it as 4 plus 2 times x minus 1 squared, that would also be fine. Everybody good with the first part of part A? Yeah. Then approximate f of 2. So 4 plus 2 times 1 squared should be 6. Easy enough? Zoom, good? Good on that? Part A?
Yeah.
Great. All right, part B, using Euler's method. starting at x equals 1, 2 steps of equal size to approximate f of 2. So the first point was, what was it, 1, 4? Yeah, 4. And I'm going to write, what was dy dx? Y times x ln x. Okay. So for the first one here, when we plug in our x value, what do we end up with? We end up with 0 as our dy dx, right? So 0 times our step, which is a half. That's, I don't know why I put 1 there. Step of a half, which tells us that this should be going up by 0. So we end up with the point 1.5, comma, 4. All right. And then our next one should be what? Our y value, 4 times 1.5 of ln of 1.5. And so what do we get when we multiply that by half? Should be 3 natural log of 1.5. Guess that's good enough. And then we'll put in our point as 2, comma 4 plus 3 ln 1.5. Good or no? No calculator, so that's your answer. Any questions on that part? Zoom, you good?
Good, Zoom.
Good. Yeah. Wonderful. All right. And what was part D? Part C. Right, it was part C. Part C was find the particular solution with that initial condition. So we're going to have to rewrite this as dy over y equals x ln x dx. Then we need to integrate both sides. Integral of the left should be easy. That should be natural log absolute value of y. Integral of the right-hand side is a little bit more difficult. What do we have to do to integrate that? We got to do it by parts. Right, so what are you going to let u equal? You want to let u equal ln x? Okay, we can do that way. That's fine. What's dv then? X. So du should be 1 over x, and v should be x squared over 2. So we end up with u times v. So x squared ln x over 2 minus the integral of v du, which should just be x over 2 dx. So we'll end up with natural log absolute value y equals x squared ln x over 2 minus x squared over 4 plus our constant. Everybody good there? Zoom, you get up to that point?
Yep.
All right, when x is 1, y is 4. So natural log of 4 equals negative 1/4 plus our constant. So our constant is 1/4 plus ln 4. Everybody good there? Yeah? Good. And then what? Plug that back in. Natural log of y, or absolute value of y, equals x squared ln x over 2 minus x squared over 4 plus 1/4 plus ln 4. And then we exponentiate. And we end up with y equals e, let's see, we'll go with 4 e to the x squared ln x over 2 minus x squared over 4 plus 1/4. Good or no?
Was it also fine if you solved for y and then solved for c, or is that Is that
Sure.
bad?
No,
Okay, cool.
I assume you got the same thing.
Sort of. I'm checking to see if it is the same, but I was good up until the C. But yeah.
Okay. How do we feel about that?
So you can solve for C at any point, and it technically shouldn't make a difference to your end product answer, right?
That is correct.
Okay.
I always prefer to solve for C immediately after I integrate, once I finish integrating, but that's just me.
Okay. Thank you.
Good or no? Jenna, you're good? Yeah. Derek, good. Ben, you good? Yeah. Noah, you good? Yeah. Good. Well, so when you clear out the absolute value, you got to make sure that you choose the right value. Either the positive or the negative. But if you plug in 1 for x, this becomes e to the 0. And so 4 e to the 0 needs to be, plug in 1, you're supposed to get 4. So it could be the negative version. So if the point was 1 negative 4, you need to put a negative there. But because the point is 1 4, it stays as positive. Yep. Good. Everybody in Zoom is good?
Yeah.
Okay. All right, let's look at this one. First off, they give us this Maclaurin series g of x, and then they don't ask us about it until part C. So we'll do parts A and B without even worrying about g of x. Part A asks us to state the conditions necessary to use the integral test to determine convergence of the series n equals 0 to infinity of 1 over e to the n. And then we'll use the integral test to show that that converges. So what are our initial conditions for the integral test? One is that it has to be positive, right? It has to be, so the series has to be positive. So we'll write this. The series must be positive, and the series must be decreasing. And the integral, or the function that we use, needs to be positive, needs to be decreasing, and it needs to be continuous. Right? The series is going to be continuous regardless. But the series itself has to be a positive decreasing series, and the function that we use for the integral must be a positive decreasing continuous function. So those are the conditions necessary for us to use the integral test. And so then we will integrate from 0 to infinity of 1 over e to the n. We'll say 1 over e to the x dx. And we'll do this on another page since there's not a lot of room here. We'll rewrite this as a limit as a approaches infinity of an integral from 0 to a. And we're going to write this as, instead of 1 over e to the x, let's write this as e to the negative x. How do we integrate e to the negative x? Yeah, add a negative for the u sub, it ends up becoming the limit as a approaches infinity of negative e to the negative x, evaluated from 0 to a. Everybody good with that? Sure. That gives us the limit as a approaches infinity of negative e to the negative a minus negative e to the negative 0. Now, what does that become? That becomes the limit as a approaches infinity of negative 1 over e to the a. And then this just becomes plus e to the 0, so just plus 1. And as a goes towards infinity, this becomes, what? This becomes 0, yeah, so the whole thing becomes 1, right? And so we've shown that the integral itself converges, therefore the series converges. I think that's all they wanted to show. Yeah, use the integral test to show that it converges. So we'll say so. The sum from n equals 0 to infinity of 1 over e to the n also converges. Mhm. What did you like? Did you write negative e to the negative a minus negative e to the 0? Or did you just go straight down to here? It's probably okay if you didn't. I would probably write one more step in there. If it were me, just to be safe, I'd probably write one more step in there. You probably don't need both of them. One of the two. I'd probably write this one. If I were to write one of the two, probably write that one. All right, everybody good there with A? People in the Zoom, you good? Yeah.
Good.
All right, part B, use the limit comparison test with the series to show that the series G of 1, oh, they did use G earlier, to show that this series converges absolutely. So what does the limit comparison test say we need to do? Take the limit as n approaches infinity of one function over the other, right? So it doesn't matter which one we really use. So let's do the limit as n approaches infinity of, it doesn't really matter, 1 over e to the n over, what was the other one? 1 over, right, but we're going to do absolute value because we have to have a positive series. So I'll put it 2e to the n plus 3. The plus 3 is not in the exponent, correct? All right, so now the absolute value is going to make this negative 1 to the n insignificant. So we really just end up with 2e to the n plus 3 over e to the n. And however you choose to write this out, there's a lot of different ways you could do it. I think the easiest way here would just to rewrite this as limit as n approaches infinity of 2 plus 3 over e to the n. And just say that equals 2. And since 2 is less than infinity but greater than 0, they either both converge or they both diverge. And since we already know that 1 over e to the n converges, then that means the other one also does by the limit comparison. Everybody good there? Good? Yeah? Yeah? Zoom, good or no?
Good.
I did the other function on top, but I still got like a half, so that should still be okay, right?
That'd be 100% fine. Half is also between 0 and infinity. So.
Okay, so same result. Okay, thank you.
All right, part C, determine the radius of convergence for G. Okay, so in order to find the radius of convergence for G, what test are we going to use? Ratio test. So we're going to do the limit as n approaches infinity of the absolute value. Let's see, I don't know what that's here. The n plus first, so negative 1 to the n plus 1, x to the n plus 1 over 2e to the n plus 1 plus 3. And then times 2e to the n plus 3 over negative 1 to the n x to the n. Right? Where did I get the x from the series? X to the n? Yeah. Good? Were you just using this one again? Yeah. They're talking about this is G evaluated specifically at 1. This is the series for G for any x time. All right. Let's see here. So what do we need to do? We need to simplify this down as much as we can. This becomes the limit as n approaches infinity. -1 to the n plus 1 and -1 to the n with the absolute value. Those are just 1, so we can ignore those. X to the n plus 1 over x to the n is just an x in the numerator. So we got x times 2e to the n plus 3 over 2e to the n plus 1 plus 3. And what does that give us here? As n goes towards infinity, this becomes, well, the x is just x, right? And what do I need to do with the 2e to the n plus 3 over the 2e to the n plus 1 plus 3? That should just become what? What? Should just become an e in the denominator, right? This becomes the, well, value. This just becomes the absolute value of x over e. Everybody good with that? Yeah, right. The 2e to the n plus 3 and the 2e to the n plus 1 plus 3. Really effectively, as we go towards infinity, the 3's are insignificant. The 2's cancel out. It's e to the n over e to the n plus 1, which is just e in the denominator. And so the ratio test says, if you get this limit over here, set it less than 1 to see what your radius of convergence is, and then get just an x plus or minus some value inside of there. Gives us the absolute value of x is less than e, so our radius of convergence is e. Good or no? Good with that, Ben? Yeah. Derek, good with that? Yeah. Zoom, good with that? It was pretty easy, serious question overall, I think. Those of you that took the May 4th test, I guess just Kevin, lucky you. Easy, serious question. All right, and then I think there was a part D, right? The first 2 terms of the series of G of 1 are used to approximate G of 1, use the alternating series error bound to determine an upper bound. Okay, so the first 2 terms of the series should be what? Well, we don't really need to, we just need to figure out the second term, right? If we're using the first 2 terms, that's fine, the second term. So G of 0, sorry, not G of 0, but n equals 0, n equals 1, we need n equals 2. So G of 1 at n equals 2 would be -1 to the n over, what was it, 2e squared plus 3. And our n was, sorry, our n was 2, right? So -1 squared. So our bound on the error ought to be 1 over 2e squared plus 3. Easy enough? Everybody good with that? I wouldn't, I would just say add, I would write this. I would write add n equals 2 and then put that. Everyone's good. Zoom, you're all good with that?
Good.
Great. Correct, Ryan. There, the alternating series error bounded error is just the term that comes after wherever you truncate. So they truncated after 2 terms at n equals 1. So our error is the next term for alternating series error bound. Anybody else? Any other questions?
Wait, could we go to number 4D?
4D. Sure, maybe. Now, is this one? Yeah.
Yeah. It's about the mean value theorem one. So you said yes, like the mean value theorem does guarantee where the average rate of change equals like 8/3, right?
The average rate of change is 8/3. The mean value.
I mean, like,
yeah, it says that the derivative of G must be 8/3 somewhere on that interval. Yeah.
wait, could you go to like the question? Isn't G not differentiable on the open interval?
The derivative of G is F, and F exists on this entire
Oh,
-4 to 2.
oh, I see, I see. I thought, yeah, sorry, I thought that was the graph of G. Okay, I understand. Thank you.
Differentiable at multiple points on that interval, but it is, but G is, because the derivative exists on this.
Right. Okay, thank you.
Anybody else? Any other questions on any of those? Oh, welcome, Nolan. So I feel like you guys are probably okay with the graph FRQs, but if you want to do another graph FRQ or two, we can do those today. Otherwise, we can just look at some more of the miscellaneous ones. Anybody have a preference? Nobody here has a preference. Zoom, do any of you have a preference?
Can we do some graph ones?
Sure. We can do another graph one. What was the last graph one we did? Anybody remember? I think it was this one. Was it this one? That was the last one we did. We did not do this one though. No. All right. There is a graph FRQ for you guys to do. Wonderful. Enjoy. Have fun. It is number 6. All right, I'll give you guys, I don't know. I'll set the timer for 15 minutes, but I'll check in before the 15 minutes is up. Ready, go. Now we're recording.
Yeah.
Okay, I'm going to go back for just a second. G of 3 was just the area from -3 to 3. -3 to 2 is positive, triangle, so find that area. 2 to 3 was negative, below the x-axis, so find the area of that triangle and subtract. Part B, we said when is G prime greater than 0 and G double prime less than 0, so F was greater than 0 and F prime is less than 0. F was greater than 0 when it's above the x-axis, but the derivative of F was only negative from -5 to -3 and 0 to 2. And then we just did this. We used the quotient rule to find the derivative, and then we plugged in 3 and got a number. Okay, cool. Part D. Another new function, p of x, f of x squared minus x. We want to find p prime at -1, I think, find the slope of the tangent line at -1. So first we'll find p prime of x, find that using the chain rule. That should be f prime of x squared minus x times the derivative of x squared minus x, which is 2x minus 1. Everybody good there? Plug in -1, gives you f prime of 2 times -3. F prime of 2 was the slope of this at 2, which is -2. We already figured that out earlier. Find that point. -2 times -3 is 6. Good or no? Graph FRQ is pretty straightforward. Feeling okay about those? Okay. Anybody else? Any other questions? Everyone's good?
Can we go back to part C for a sec?
Sure. You have a question on it, or you just want to look at it?
Yeah. Why didn't you multiply stuff in the numerator by 5? And then in the denominator, why isn't it 25x squared?
Cancel out all those 5s.
Ah, okay, I see.
That 5x squared instead of 25x squared, and then simplify with 5.
Okay, neat. Thank you.
Yep. Sure, there's the graph. You have a question on it, or you just? Oh. Yeah, I mean, you know what you're doing. That's a math. X squared minus 2. Yeah, that's not what that is. You probably won't do that when it's sitting there right in front of you on the test. All right. Let's see. We got, what do we got? We got time. Well, I don't know. What do we got time for? We don't really have time to do another one. I don't know. I'll give you guys time to do one of the miscellaneous ones. I don't think we need another graph one. I think we're pretty good with those. I'll give you some time to work on the miscellaneous, and then when we have time after the quiz tomorrow, we'll do some more of the miscellaneous ones. We did the graphs one, right? Did we do the coffee? No, we did a tea one, didn't we? We did the tea one. We did the tea one. Let's do a zoo. No. Ooh, let's do this one. This will be a good one. It doesn't really require any BC stuff though. Let's do. The problem is these are all too easy. No. You don't need to know. They'll give it to you if you need to use it. Yeah, let's do this one. I like this one. It's not too bad, but I like part D in particular. So. All right, ready? Go.